Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this lecture is entitled Derivatives of Inverse Trigonometric Functions and Such. Let's review the definitions briefly. We say y is equal to the arcsine of x if and only if the sine of y is equal to x. This certainly is the range of the sine function, so it's the domain of the inverse. And this is a restricted range or set of values for y, and it's restricted so that the function is 1-to-1. That means there is an inverse. It is important for students not only to remember this part of the definition, but remember these restricted values. Those are values your calculator will give you, and sometimes as engineers you have to make different sense of the values that you get depending on the problem. We say y is equal to the arc cosine of x if and only if the cosine of y is equal to x. Again, we have this, but notice that the range is different because the cosine is 1-to-1 in a different space on the real number line than the sine. So these are the conventions. We say y is equal to the arctangent of x if and only if the tangent of y is equal to x. Notice that this is different because you have an unbounded set of values that the tangent function does take on, and the range does not include the places where it goes to minus infinity and plus infinity. So this is open intervals. Now we continue going on to these other functions. I'm going to ask you to review those yourself, but these are the ones that we probably will be focusing on most in our examples, but the other ones do exist. On your calculator, a different notation is used than arcsine, and you see on your calculator they will call it the sine inverse, the cosine inverse, and the tangent inverse. That does not mean that is 1 over the sine of x. That means it's the inverse function. It's not really great notation. To get at this with this calculator, you have to press the second button here. Another button that's important to know about is you do want to be careful what mode you're in when doing trig functions, because you can either be in radians or degrees, and how you interpret those answers is radically different. You learned about graphs of those functions, and notice that where you had horizontal asymptotes with the trig functions, you have, where you had vertical asymptotes with the trig functions, you have horizontal asymptotes with the inverses. Let's talk about evaluating some inverse trig functions. Again, this is review, that's why I'm going straight through the examples. So you want to evaluate all of these calculations. Now the first three are things that you might run across in a calculator-less part of an exam, because these are special triangles. These are either the 30, 60, 90 degrees special triangles, or the pi over 4, and pi over 2 special triangles. And so commit those to memory. Again, those are unit circle considerations. Okay, so let's do this. Y is equal to the arcsine of minus 1/2. That means the sine of y is minus 1/2, and we have to be in this interval. So that means that the answer is minus pi over 6. The next one, y is equal to the arc cosine of 0, means that the cosine of y is equal to 0, and this is the interval we're working in. So that means that the answer is pi over 2. If we say y is equal to the arctan of the square root of 3, that implies that the tangent of y is the square root of 3, and the answer is in this interval. And so you know from your special triangles that is pi over 3. Now, this one is not a special triangle. You have to use a calculator. I used the calculator over here. I pressed the buttons I showed you, and the inverse sine of 0.3 is 0.3046 and change, and your author rounded that out to 0.305. Now, inverse functions have the property that if you take the inverse followed by the function, or the function followed by the inverse, you get back to where you started with. But when applying these properties to inverse trig functions, remember that the trig functions have inverse functions only in restricted domains. For x values outside of these domains, the properties do not hold. You have to be careful. For example, the arcsine of the sine of pi is 0, not pi. But if you're within the domains, these functions do hold. And there are similar functions for others. We sometimes use these to solve an equation. So here we have the arctangent of this business is pi over 4. I'm going to take the tangent of both sides. And since I know the arctangent is between minus pi over 2 and pi over 2, I know that when I take the tangent of this, I'm going to get what I started out with. And I know this from my special triangles that the tangent of pi over 4 is 1. So I can solve that and I get x is equal to 2. We also can use right triangles. Suppose you are given that y is equal to the arcsine of x, and y is a number between there. That means that you have an acute, that means you can think about this as it's an acute angle, but that means that you can think of it as being a right triangle. We want to find the cosine of y. Well, if we know y is equal to the arcsine of x, that means x is equal to the sine of y. So I have y here. The sine is opposite over hypotenuse. So I know two sides of the right triangle. That means I can figure out what this side is using the Pythagorean theorem. And I wanted to find what cosine of x is. So cosine of x is going to be this adjacent over the hypotenuse, and that's the answer that you see here. Here we're saying that y is equal to the arc secant of the square root of 5 over 2. Now y equal the arc secant of square root of 5 over 2 means that the secant of y is square root of 5 over 2. So y is sitting here. The secant is the reciprocal of the cosine. So it's going to be the hypotenuse over the adjacent. And then I can use the Pythagorean theorem to figure out that this is 1. Now the problem then asks us to find the tangent of this y. Again, the tangent is going to be the opposite over the adjacent, or it's going to be 1/2. If you find yourself struggling with this, I'm going to suggest that you go and visit the do-it-yourself reviews in the Learning Commons. They're very good, or you can go work with the Learning Commons and people in the Math Systems area as well. Now recall previously we actually did some of this inverse function business because we knew that the logarithm and the exponential were inverse functions of each other. So if we say y is equal to the natural logarithm of x, that means that e to the y is equal to x. Then we differentiated this implicitly and solved for dy dx and realized that e to the y was x. So we learned that the derivative of y is equal to the natural logarithm of x was 1 over x. In a similar way, we can say y is equal to the arcsine of x. That means that the sine of y is equal to x. And now we're going to take the derivative implicitly with both sides. So when we do it on this side, we will get 1. When we do it on this side, we will get the derivative of the sine is the cosine by the chain rule dy dx. And we'll solve for dy dx, we divide both sides. So we'll get 1 over the cosine of y. But the cosine in the within the domains and ranges that we were talking about is going to be positive, and so that means that we're going to have 1 over the positive square root of 1 minus sine squared y by a trig identity, and the sine of y was x, so this is 1 over the square root of 1 minus x squared. So if y is the arc sine of x, the derivative is going to be 1 over the square root of 1 minus x squared. Similarly, if y is the arctan of x, then the tangent of y is equal to x. I'll take the derivative of both sides with respect to x. The derivative of this side is going to be 1. The derivative of the tangent of y is secant squared y times dy dx. So I will divide both sides by secant squared, which is never 0. And I will use a trig identity to write it this way. But 1 plus tangent squared y is really the same as 1 over 1 plus x squared, because the tangent of y was equal to x. Let's look at one more example of this. Y is equal to the arcsecant of x. That means that x is equal to the secant of y. We're going to take the derivative of both sides. So the derivative of the secant y is going to be the secant y, tangent y, dy dx, and the derivative of x is going to be 1. So we're going to divide all the way through by secant y tan y, and what happens is that we will have that, and that means that dy dx is going to be secant y, but this is a trig identity for the tangent of y. And by the way, there is an absolute value that kind of is not showing up in these notes, but you do have to be concerned about the SIGN of these things, and so we do have an absolute value popping up. But secant of y was x, and so dy dx then is going to equal 1 over, this really should be the absolute value of x times the square root of x squared minus 1. So that's the derivative formula you're going to be memorizing. And you also have other derivative formulas that you memorize, although we're not going to derive those here. In your exercises, I'm sure you do derive those. Okay, so here's some derivatives. We want to practice those things, and you know what to do. And I will see you in 20.1, and we'll go over